Welcome back, student, to yet another lecture of pipe flow. Last time we finished talking about the entrance region, and now we are going to see what the pressure and the shear stress distribution through a figure, through a graph in the both the entrance region and the fully developed flow region is. So when the as you see in this graph, as soon as the water enters the pipe, there will be a pressure drop here, and that is called the entrance pressure drop. This is LE, as we said, and this value can be calculated based on the Reynolds number. If the flow is laminar, it is 0.06 RE, whereas if it is turbulent, it is of the order of RE to the power 1 by 6. However, you see, after the flow has become fully developed, the pressure dP dx, the pressure drop per unit length becomes constant. So this has been obtained through experimental analysis. So del P del x is equal to constant. So important information to grasp from this particular slide is that in the entrance there is an entrance pressure drop, whereas when it becomes the flow becomes fully developed, del P del x is constant. Here in the entrance flow, what happens is the pressure is balanced by the viscous forces and the acceleration in the entrance region, all right. Whereas in the fully developed flow there is no acceleration, all right, no acceleration. Therefore the viscous forces are balanced only by the pressure drop, all right. So one thing that distinguishes fully developed flow and the entrance flow is that the existence of acceleration in the entrance flow region compared to the fully developed flow region. Now the need of this pressure drop, can be seen as, in terms of force balance, it can be said that the pressure force is needed to overcome the viscous forces generated, all right. In terms, if we want to see why the pressure is needed to be dropped, so pressure force is needed to overcome the viscous force generated, whereas in terms of energy balance we can say that the work which is done by the pressure forces is needed to overcome the viscous dissipation throughout the fluid. So these are the two different ways of seeing the need of the pressure drop in the fully developed area, and the same can also be applied for an entrance region, just that the instead of only viscous forces, it will be viscous forces plus the acceleration. So now the problems with the fully developed laminar flow is that the basic problem is that in reality most of the flows are actually turbulent. Therefore the theoretical analysis is not yet possible, all right. Second thing, most of the pipes that we see in our network are not long enough to allow the attainment of fully developed flow, because if you see, it was LE by D is equal to 0.06 RE. In case of, let us say, a Reynolds number of 4000, which is pretty common, this LE, and diameter of the pipe, let us say 1 meter, 0.06 into 4000, so LE becomes 240 meters. So the entrance length region is 240 meters for a pipe of diameter 1 and Reynolds number of 4000. Even if the Reynolds number is 1000, then also it will require at least 60 meters length pipe. So in most of the cases what happens is these pipes are not long enough to allow attainment of fully developed flow, because for that fully developed part we can actually do the real analysis, but that will occur only after the fully developed region has occurred, which in most cases does not, because the pipes are shorter in length. Now, but what is the importance of the fully developed laminar flow? There are certain problems related to it, but there are certain importances and advantages to it as well. It is one of the very few theoretical viscous analysis that can be carried out exactly, and that we will see how in our upcoming slides and lectures. And therefore, it also provides a foundation for further complex analysis. There are many practical situations which involves the use of fully developed laminar pipe flow. We will see those examples later. So, the equation for fully developed laminar flow in pipe can be derived using three approaches. What are these three approaches? One is from Newton's second law, which is applied directly. Second is from using the Navier-Stokes equation. The third one is from dimensional analysis. All right. So, what we are going to do? We are going to start the derivation of fully developed laminar flow in pipe using Newton's second law. Now, so this is the snapshot of a fluid element at time t. All right, this one here. Okay, and in the fully developed laminar flow, this is the velocity profile as we have seen in our laminar and turbulent flow analysis, and this velocity is only a function of radial distance r from the pipe. All right, this is the diameter d of the pipe, this is the x dimension, and the fluid element is of length L that we have considered. At time t is equal to t plus delta t, so therefore after at a time interval of delta t, this is the fluid element. All right, this is section 1 and this is section 2. All right, so you have to keep this figure in mind. So, for your easiness, I have already kept this figure here so that you are able to follow the derivation. Now, I will repeat what I have said again. We have considered a fluid element at time t as is shown in the figure above. This element, it is a circular cylinder of fluid of length L and radius r, centered on the axis of the horizontal pipe of diameter d. Because the velocity is not uniform across the pipe, the initial flat end of the cylinder of fluid at time t becomes distorted at time when the fluid element has moved to its new location, and the reason is because across the radial distances the velocity is not constant, it is a function of radial distance. If the flow is fully developed and steady means that it is not a function of time, the distortion on each end of the fluid element is the same and no part of the fluid experiences any acceleration as it flows. So, this is the background for the derivation containing important information that will be used during the derivation. So, there are some assumptions. The assumptions is that the local acceleration is 0 since the flow is steady. We also assume that the convective acceleration is 0 since the flow is fully developed. Now, every fluid particle flows along a streamline with constant velocity. The neighboring particle have slightly different velocities because the velocities are a function of radial distance r. For now, the gravitational effects will be neglected, and the pressure is constant across any vertical cross section of the pipe. So, of course, the pressure varies from this point to this point to this point to this point to this point, but across this cross section the pressure, if there is a pressure P here, it will be P here, it will be P here, P here. So, pressure is dependent, I mean changes only with the x distance, not with the r distance. Now, the pressure drop delta P is equal to 0, that means pressure decreases in the direction of flow, and that is very true. The water will move from a pressure from the region of having high pressure to that having low pressure. All right. So, this is the figure for that element that we have drawn. So, the force acting from this side, if there is a pressure P1 on the left side at section 1 and this is section 2, and if we assume that delta P is the pressure drop, so P will be here will be P2 is going to be P1 minus delta P, right. And because of the viscous forces, if there is a shear stress acting called tau, then the force acting F1 will be pi 1 pressure into area. Similarly, the another force will be acting here F2 P2 into area, and this is the shear stress force due to shear stress. All right. So, the equation is going to be F1 minus F2 minus the tau into 2 pi RL, because this shear stress will be acting on the entire cylindrical parameter. So, F1 is P1 pi r square, F2 is, so F1 is this, F2 is P1 minus delta P into pi r square minus T into 2 pi RL is equal to 0. All right. So, just going, so it will be P1 pi r square minus P1 pi r square plus delta P pi r square minus tau 2 pi RL is equal to 0. So, expanding, so this gets cancelled. So, we can write tau into 2 pi RL is equal to delta P pi r square. So, this r and this r gets cancelled, pi and pi gets cancelled. So, delta P can be written as, so delta P by L. So, if L we bring this side, so delta P by L can be written as 2 tau by, and this r we bring downside here. This is exactly same as we have written here. All right. So, we get delta P by L is equal to 2 tau by r. See, the pressure drop per unit length does not depend on, so this delta, sorry, so this delta P by L does not depend upon the radius, right, because it's pressure drop per unit length, and this we call as equation number 1. So, we can say, so you see we can say that delta P by L was constant, right. So, we can say tau is equal to, so we have got 2 tau by r is equal to C1, or we can simply say tau is equal to C into r. All right. This is what we can get. This is C1. So, but 2C is 2C1, C1 by 2. So, tau we can write CR. All right. So, we see that at midpoint at r is equal to d by 2, this tau takes C d by 2, and that is the maximum, and that happens where? It happens at the wall. Therefore, this shear stress tau at wall is called as tau W. wall shear stress. All right. So if we put R is equal to D by 2 in this equation, see, so what do we get? Tau is equal to, so tau is equal to C into D by 2. All right. And this C is going to be 2 tau W by D. All right. Therefore, tau can be written as 2 tau W R into D. All right. And when we have obtained tau, we can write delta P, because delta P by L is equal to 2 tau by R, or 2 by R, or we can write D by 2 here, and tau is 2 tau W R So this R and R gets cancelled, so this becomes delta P by L is equal to 4 tau W by D, and delta P comes 4 tau W into L by D, this same equation. All right. Now you would have a question that how did we get C? So let's see, just going back a little bit, you might have a question how this C becomes 2 tau W by D. How? So see, we have written tau is equal to CR, so at R is equal to D by 2, tau is equal to tau W, correct? So we substitute this in this equation here, we get tau W is equal to CD by 2. All right, so C becomes 2 tau W by D, and this is what has been substituted here. All right. So we get tau as a function of the wall shear stress, 2 tau W by D into R. So now we have obtained tau in terms of wall shear stress. Therefore, using this particular equation, we have obtained delta P. So these are some of the important results to remember. This tau is equal to 2 tau W R by D is equation number 2. As you can see, that tau is a function of R, and this pressure drop per unit length is constant as 4 tau W by D. All right. So this is the profile, you see. So this is the laminar profile for viscous pipe flow, and this is the ideal profile. You see, this is VC. You remember in our laminar and turbulent fluid flow, we derived this, that VC was VC by 2, the average, the ideal in viscid profile, whereas it goes from 0 to VC. All right, and the shear stress variation is like this. Okay, this is the laminar profile in the pipe flow, and the shear stress distribution is like this. This is something important to remember as well. Now the discussions. Shear stress varies linearly with R, and why? If the viscosity was 0, that there was no shear stress and pressure would have been constant throughout the channel. Therefore, a small shear stress can produce larger delta P if the pipe is relatively long. This you have to know why shear stress varies linearly with R. Of course, we have done the derivation, but you try to find out. So, take it as a homework question. All right. Secondly, if there was no viscosity, assume, let us say if it was 0, then there would be no shear stress and pressure would have been constant throughout the channel. That is true, because there would be nothing that would cause the pressure to work. Therefore, a small shear stress, you see this, delta P is 4L tau W by D, right. See this equation and see our conclusion, that a small shear stress can produce large delta P if the pipe is relatively long. So, if L by D is very much greater than 1, then even a small shear stress will produce large delta P. So, until now what the analysis we have done is valid for both laminar and turbulent flow. At no point in time we have assumed that the flow yet is laminar. Okay. So, the assumptions for both laminar and turbulent flow is same. So, all the equations, equation number 1, equation number 2 and equation number 3 are valid both for laminar and turbulent flow. All right. So, from here onwards we would assume the shear stress distribution for laminar flow. So, from now on in the next derivation we would assume that the shear stress distribution is for the laminar flow. So, for Newtonian liquid, for laminar flow, this is the shear stress distribution we have seen. Tau is written as minus mu du dr. You remember this? All right. And this is what we have got, right. Tau is equal to, how did we get this equation? We get this equation from our equation number 1. So, this is equation 1. All right. So, taking both together we can see we equate these two and this becomes minus mu du dr is equal to delta P by 2L into R. So, we equate this one and we equate this one. All right. So, du dr can be written as minus of delta P by 2 mu L into R. All right. So, if we take dr on this side, it will become du is equal to minus delta P by 2 mu L R dr. Therefore, we can simply write integrate on both sides. We get u is equal to minus delta P by 2 mu L with minus sign and R square by 2 plus C1. So, finally, it can be written as minus delta P by 4 mu L R square plus C1, and this is the same thing that we have written here. All right. If you can follow this. All right. Now, importantly, there is one boundary condition at. So, one of the boundary condition is no slip condition, and where does it happen? It occurs at the wall, or wall is where? At R is equal to d by 2, which means u is equal to 0 at r is equal to d by 2. And if we put this in this equation, let's put it, we say 0 is equal to minus delta p by 4 mu l d square by 4 plus C1. All right. So what do we get? We get C1 as delta p d square by 16 mu l. All right. So this is the value of C1 that we get, and if we substitute this C1 here, let's do that. So I'll rub these. So u will be minus delta p by 4 mu l into r square plus C1 is delta p d square by 16 mu l. This r square can be written as d square by 4. Therefore, if we take delta p d square by 16 mu l as constant, sorry, so this is not d, this is r square. So let me, okay, so this is r square so u is, so let's take delta p d square by 16 mu l as constant, and then we are left with 1 minus, so this will be 1 and this will be r square divided by d square by 4, or exactly same all right. So this is what we get. So we have got u r as a function of radial distance r. So the flow rate is going to be, so now we have determined u as a function of r, right, and the flow rate across the entire pipe will be integral of 2 pi r dr. You see the area, if we start integrating at a distance, we take an element of thickness dr at a distance r, we can write q will be u integral dA, all right, and we integrate from r is equal to 0 to d by 2, that the half, I mean the entire radius, we can write u r into 2 pi r dr. So integral 0 to d by 2, u r was delta p d square by d square by 16 mu l into 1 minus 2 r by d all right into 2 pi r dr. Okay, and on integration we will come up with this equation, pi d to the power 4 delta p by 128 mu l. This is the flow rate q in the entire pipe. All right, this is termed as equation number 4, and this particular flow rate q is called the Poiseuille's law. So we have used Newton's second law to derive the discharge rate through a pipe as a function of pressure gradient delta P, and this is Poiseuille's law. Okay, so this is an important topic about, there's an important topic, that the Poiseuille's law. So one of the critical one to this laminar the laminar flow through pipes. So I think we will finish this lecture at this particular point. When we meet again in the next lecture, we see how these laws can be modified if the gravity is also present, and proceed further with our analysis. So thank you so much for listening and attending today's class. I will see you in the next lecture.